In this video, I want to talk a little bit about the reactions of carboxylic acids, aside from their ability to donate a proton as an acid. One of the things we can do is a reaction very similar to the formation of acetals that we looked at with aldehydes and ketones, and that is the acid-catalyzed addition of an alcohol. And actually, it's a substitution of the OH group for a alcohol group, which leads to the formation of an ester. This is referred to as the Fischer esterification, after the chemist who discovered this reaction. So this mechanistically is very similar to the formation of an acetal. The first step is activation of our carboxylic acid by protonation of the carbonyl to form a cation intermediate. A weak nucleophile such as alcohol can add to that carbonyl, pushing the electrons up onto the oxygen to neutralize the charge, forming a protonated alcohol group on the carbon that is deprotonated by the conjugate base to reform our acid catalyst, which can be used later in the reaction. That generates this intermediate, which looks a lot like the hemiacetal if this OH group were not an OH but a hydrogen or carbon. This is an OH, however, and that's prone to be protonated. If it protonates on one of the OH groups, we form the protonated species, which could break to lose water, and that's the byproduct in this reaction, water, to form this cation intermediate, or we can draw it with the double bond to the oxygen. Deprotonation of that leads to the formation of the neutral ester product. So this is a way to make esters from carboxylic acids under acid catalysis. If you're interested in the details, this slide shows the acid-catalyzed hydrolysis of the ester to the acid. Again, very similar steps: protonation of the carbonyl to form a cationic intermediate, addition of neutral water, a removal of the proton to get to an intermediate, protonate the group that's going to leave, in this case the OCH3, break the bond from that cationic species to form alcohol that deprotonates to form our acid product. Now that works really well if you have simple situations where you have lots of water or lots of alcohol. You can drive the reaction to the right or to the left. However, it's really not the best way to do a hydrolysis of esters. The best way to do that is to use a base catalyzed hydrolysis, where you take something like sodium hydroxide and react that with an ester that will attack the carbonyl to form this anionic intermediate. The negative charge will come back down to form a double bond and kick off OCH3- as a leaving group. Now, because of the pKa difference between alcohols and carboxylic acids, this will be immediately deprotonated by the OCH3- to form essentially an irreversible reaction, the carboxylate and the alcohol. And that's what drives this reaction to the right so readily, is formation of a step which is now irreversible within the confines of the reaction. If we want to get to the acid product, you simply add something like HCl or neutralize that negative charge by adding some other acid to it to get the carboxylic acid at the end. This base catalyzed hydrolysis of esters is what we call saponification, and it's used to make soap. Soap is made by the hydrolysis of fats, and fats are triesters of long-chain fatty acids. So if you react this with sodium hydroxide, this reaction would produce the sodium carboxylate salts of those fatty acids, and these in water will tend to form these micelle structures where the ionic polar head group is solubilized by the water, and inside that is an interior that's not water soluble but organic, and it's this interior organic part which dissolves the grease which holds dirt onto things and allows us to wash it away in water using these micelles. That's how soap works, and soap is reliant on this hydrolysis of esters to carry out the formation of the soap ions. In the previous example of hydrolysis, we saw that an alcohol group is substituted for an OH group in a carboxylic acid derivative, and this is a reaction which is much more general and common among the acid derivatives, and things like acid chlorides, acid anhydrides, esters, and amides all can undergo substitution reactions to different degrees. Now, certainly some are more reactive or less reactive, and they're listed in the order of reactivity here. This reaction proceeds through what we call a nucleophilic acyl substitution. So we are doing a substitution of a nucleophile for a leaving group, but it's going through an acyl carbon. That is, it's attacking a CO double bond to generate first a tetrahedral intermediate, and then because we have a group which could depart, that double bond is reformed, kicking off our leaving group to form the substituted product. So in this case, we've exchanged a generic Y group for a generic nucleophile through this two-step process. Various acid derivatives have different reactivities due to two reasons. One is the electron withdrawing properties make the carbon more plus charged in order for the nucleophile to react faster, and also the leaving group ability of that group matters a lot in the second step. So not only do we enhance the rate of the first step by making it more electron withdrawing, we enhance the rate of the second step by stabilizing the leaving group as it comes off as a more stable anion. So chlorides are the most reactive of the acid halides. Carboxylates, or the acid anhydrides, are almost as reactive as acid chlorides, and these tend to react very readily with all kinds of nucleophiles, both neutral nucleophiles as well as negatively charged nucleophiles. Esters are significantly more stable but can do these reactions, and amides are the most stable of all, and that's because the lone pair of the nitrogen donates into the oxygen, reducing the amount of plus charge on the carbon, as well as being a very, very poor leaving group. The same thing with the oxygen. It has also some donating ability. So in terms of reactivity towards nucleophilic acyl substitution, it's most reactive at the halides and gets less reactive as you move to the right. Because of those reactivity differences, we can easily convert more reactive acid derivatives into less reactive acid derivatives with the right nucleophile. So a chloride could be substituted with a carboxylate in order to convert a chloride into an anhydride. But you can't do it the other way around. It's very difficult to go from a less reactive to a more reactive acid derivative. You could take the same acid chloride and make an ester from it by reacting with an appropriate alcohol. You could also do that from an anhydride. And so as you get less reactive, you can go downhill in terms of the reactivity and make more stable products. So if you take an acid chloride and react it with an amine, such as ammonia, you can make an amide. You can do the same thing with an anhydride or with an ester, but you can't go back. The one thing that we can do with all of these is to hydrolyze them under various conditions. Some take more heat and energy to do it than others, but adding water or doing a substitution with water under acid or base catalysis allows you to take any of these derivatives and form the carboxylic acid. So we can take any of these derivatives and regenerate the carboxylic acid that it was made from initially. And fortunately, although we can't take any of these more stable acid derivatives and make the most reactive acid chlorides from them, we can easily make acid chlorides directly from the carboxylic acids. This process of taking a carboxylic acid and making an acid chloride is easily done using phenyl chloride, just like we saw in the alcohols chapter to convert an alcohol into a halide. We can take a carboxylic acid, react it with SOCl2, and it will substitute the OH group for a Cl. And if you're interested in the mechanistic details, I've drawn them here for your information. So this allows us access to all kinds of acid derivatives, and we can convert from one to the other. We can take more reactive ones into less reactive ones. We can take any of those, convert them to the carboxylic acid, and make the most reactive acid chloride again using this reaction. So in general, this nucleophilic acyl substitution reaction can occur on all kinds of different derivatives. We might need to have different catalysts or different conditions in terms of providing heat energy. However, all of them can undergo different kinds of reactions. If we add water, for example, we can do hydrolysis reactions, chloride, anhydride, esters, amides. If we add alcohols, we can take more reactive acid derivatives into esters. We refer to that as alcoholysis. We can make amides by reacting acid derivatives with amine compounds such as ammonia to make amides. We call that aminolysis. We could even add hydride reagents, which we talked about in the ketone and aldehydes chapter, or something like a Grignard reagent. The only difference between reacting an acid derivative with a Grignard reagent versus aldehyde or ketone is it will add once to break the carbon-oxygen bond, but then the leaving group will leave. So we can add a group and then reform the double bond by kicking off the Y. Once we have this, we know ketones react. A second Grignard reagent will react again. And so what we'll end up doing is actually adding two Grignard reagents to the carboxylic acid derivative. So unlike an aldehyde or ketone, it doesn't stop after one addition because you reform the CO double bond and then it reacts a second time. Well, making amides is often done from using other acid derivatives which are more reactive than it. It's actually quite difficult to make amides directly from carboxylic acids. If you take a carboxylic acid and react it with something like ammonia, the only thing that will happen is an acid-base reaction because of the basicity of amines. So you'll just simply deprotonate the carboxylic acid and form, in this case, an ammonium salt of that carboxylic acid. So if you take acetic acid and react it with ammonia, you'll make ammonium acetate. If you heat this up to very high temperatures and high pressures, you can get amides to form, although it's not the most efficient way to do it. However, some industrial processes do utilize this to make molecules. And if we take the diacids, such as the hexane dioic acid, or commonly called adipic acid, react that with the 6-carbon chain diamine compound, which we call hexamethylene diamine, or 1,6-hexane diamine. We can make polymer chains of this, which we refer to as a polyamide. And these polyamides are what we call nylons. So this 6-carbon and 6-carbon polyamide is called nylon 6,6, and this is the nylon that's used to make fibers and fabric. Well, amino acids are carboxylic acids as well, but they have both an acid group and an amino group. These groups act like an internal acid and base. So if you have a pure bottle of an amino acid, it actually exists as the salt, where we have the nitrogen is protonated by the carboxylic acid. Overall, it's a neutral molecule. However, there is a plus charge and a negative charge separated in this molecule. We refer to this as a Zwitter ion, meaning having dual charges in the same molecule. Amino acids are constituents of proteins and obviously part of our biological processes, and there are many kinds of amino acids. The common amino acids that we use to make up proteins in our bodies are alpha amino acids, meaning the nitrogen is attached adjacent to the carboxylic acid on the carbon right next to it. The simplest one of all is the 2-carbon group we refer to as glycine. You can have various substituents which are all aliphatic hydrocarbons, alanine, valine, leucine, isoleucine, proline, for example. Those can have different functional groups on them. As you can see here, oxygens, sulfurs, amide groups could be placed on there. You could have aromatic substituents such as phenylalanine, tyrosine, or tryptophan, as well as you could have other kinds of groups which are acidic or basic, such as aspartic acid or glutamic acid. They have a carboxylic acid as a side chain. Lysine, histidine, and arginine have more basic amino groups as their side chain. But all of these are constituents of proteins. The way proteins are formed are by making amide bonds between an amino group of one amino acid and a carboxylic acid group of the other amino acid. So for example, if we take alanine and valine and mix them together, you could do this in a couple of different ways. If you take the carboxylic acid of alanine and the amine of valine and connect them to make an amide bond, this is called an alanine-valine dipeptide. It's 2 amino acids which are linked to form an amide from one of the amino groups and one of the carboxylic acid groups. So notice that in this case, the free nitrogen on the left is next to the CH3 group. The free acid on the right is next to the other amino acids group. We could link this together in the other way. If we take valine now as the carboxylic acid partner and alanine as the nitrogen partner, we form a different dipeptide where the free amino group is next to the larger substituent and the free acid group is next to the methyl substituent. These are 2 different molecules made from the same 2 amino acids, just connecting them differently with regards to which is contributing the acid part of the amide and which is contributing the amine part of the amide.